In this section of the MEC study group, we will be covering the topic of maintaining a power plant and boilers. Approximately 11% of the questions asked on the MEC exam will be on the area of maintaining power plants and boilers, which means that about 11 of the 100 questions will be about the concepts of analyzing and treating boiler water, monitoring boiler systems, firing boilers on alternate fuel, cleaning boilers, preparing boilers for inspection, firing boilers, and shutting down boilers. The candidate should know the characteristics of steam, the types of steam piping systems and function, how steam traps work, basic water treatment, how infrared testing is used, the function and use of pressure-reducing valves, that heat is measured in BTUs, or British thermal units, how emergency generators operate, how to safely fire a boiler, how condensate systems function, the various types of steam valves, and how efficiency of a boiler can be improved. These tasks come directly out of the MEC test preparation manual. The first area of knowledge to understand is the characteristic of steam. Steam is the technical term for water vapor, the gaseous phase of water, which is formed when water boils. Steam tables, as currently shown on the screen, contain thermodynamic data for water or steam and are often used by engineers and scientists in design and operation of equipment where the thermodynamic cycles involving steam are used. Additionally, thermodynamic phase diagrams for water or steam, which are now overlaid on the screen, may be useful to show the various phases of steam. As water is heated from 0 degrees Celsius to its saturation temperature, its condition follows the saturated water line until it has received all of its liquid enthalpy. If further heat continues to be added, the water changes phase to a water vapor mixture and continues to increase in enthalpy while remaining at saturation temperature. As the water vapor mixture increases in dryness, its condition moves from the saturated liquid line to the saturated vapor line. Therefore, at a point exactly halfway between these two states, the dryness fraction is 0.5. Similarly, on the saturated steam line, the steam is 100% dry. Once it has received all of its enthalpy by evaporation, it reaches the saturated steam line. If it continues to be heated after this point, the pressure remains constant, but the temperature of the steam will begin to rise as superheat is imparted, which is C through D. The saturated water and saturated steam lines enclose a region in which a vapor-water mixture exists, which is wet steam. In the region to the left of the saturated water line, only water exists, and in the region to the right of the saturated steam line, only superheated steam exists. The point at which the saturated water and saturated steam lines meet is known as the critical point. As the pressure increases towards the critical point, the enthalpy of evaporation decreases until it becomes 0 at the critical point. This suggests that water changes directly into saturated steam at the critical point. Above the critical point, the steam may be considered as a gas. The gaseous state is the most diffuse state in which the molecules have an almost unrestricted motion, and the volume increases without limit as the pressure is reduced. The critical point is the highest temperature at which water can exist. Any compression at constant temperature above the critical point will not produce a phase change. Compression at constant temperature below the critical point, however, will result in liquefaction of the vapor as it passes from the superheated region into the wet steam region. The critical point occurs at 374.15 degrees Celsius and 221.2 bar for steam. Above this pressure, the steam is termed supercritical and no well-defined boiling point applies. It should be noted that because of the characteristics of steam, steam is often used for sterilization. An autoclave, which uses steam under pressure, is used for this purpose. Steam, especially dry, highly superheated steam, may be used for antimicrobial cleaning, even to the levels of sterilization. Steam is a non-toxic antimicrobial agent. For additional detailed information, please visit the link shown on the screen. The Spirax-Sarco website has a vast array of steam knowledge on their resource section of the website and is a great resource for anyone reviewing steam properties. The next section is on the types of steam piping systems and their functions. In the oldest modern hydronic heating technology, a single pipe steam system delivers steam to radiators where the steam gives up its heat and is condensed back to water. The radiators and steam supply pipes are pitched so that gravity eventually takes this condensate back down to the steam supply piping to the boiler, where it can once again be turned into steam and returned to the radiators. Single pipe systems are limited in both their ability to deliver high volumes of steam, that is heat, and the ability to control the flow of steam to individual radiators, because closing off the steam supply traps condensate in the radiators. Because of these limitations, single pipe systems are no longer installed. In two pipe steam systems, there is a return path for the condensate, and it may involve pumps as well as gravity-included flow. The flow of steam to individual radiators can be modulated using manual or automatic valves. Now on the screen, you can see a fully integrated system with chilled water being supplied to an air handler for cooling capabilities and steam being supplied to allow for heating hot water or heating capabilities in the air handler. Note that steam can also be used to provide humidification in an air handler when conditions require it. We are now going to review how steam traps work. One of the best ways to understand steam traps is to see them in action. TLV.com, as indicated by the website on the screen, provides animations of steam traps, including the float type, disc type, thermostatic type, and many others. MEC applicants taking the time to review this website will be well served with an extensive amount of steam trap knowledge. Some of the most common traps are covered in the next slides. The thermodynamic trap is an extremely robust steam trap with a simple mode of operation. The trap operates by means of the dynamic effect of flash steam as it passes through the trap, as depicted on the screen. The only moving part is the disc above the flat face inside the control chamber or cap. On startup, incoming pressure raises the disc, and cool condensate plus air is immediately discharged from the inner ring under the disc and out through the three peripheral outlets, shown in Figure 1. Hot condensate flowing through the inlet passage into the chamber under the disc drops in pressure and releases flash steam moving at high velocity. This high velocity creates a low pressure area under the disc, drawing it towards its seat, shown in Figure 2. At the same time, the flash steam pressure builds up inside the chamber above the disc, forcing it down against the incoming condensate until it seats on the inner and outer rings. At this point, the flash steam is trapped in the upper chamber, and the pressure above the disc equals the pressure being applied to the underside of the disc from the inner ring. However, the top of the disc is subject to a greater force than the underside, as it has a greater surface area. Eventually, the trapped pressure in the upper chamber falls as the flash steam condenses. The disc is raised by the now higher condensate pressure, and the cycle repeats as shown in Figure 4. The float type trap operates by sensing the difference in density between steam and condensate. In the case of the trap shown in Figure 11.3.1 on the screen, condensate reaching the trap will cause the ball float to rise, lifting the valve off its seat and releasing condensate. As can be seen, the valve is always flooded and neither steam nor air will pass through it, so early traps of this kind were vented using a manually operated cock at the top of the body. Modern traps use a thermostatic air vent, as shown in Figure 11.3.2. This allows the initial air to pass whilst the trap is also handling condensate. The inverted bucket steam trap is shown on the screen. As its name applies, the mechanism consists of an inverted bucket which is attached by a lever to a valve. An essential part of the trap is the small air vent hole in the top of the bucket. Shown on the screen is the method of operation. In step 1, the bucket hangs down, pulling the valve off its seat. Condensate flows under the bottom of the bucket, filling the body and flowing away through the outlet. In step 2, the arrival of steam causes the bucket to become buoyant. It then rises and shuts the outlet. In step 3, the trap remains shut until the steam in the bucket has condensed, or bubbled through the vent hole to the top of the trap body. It will then sink, pulling the main valve off its seat. Accumulated condensate is released and the cycle is repeated. In step 2, air reaching the trap at startup will also give the bucket buoyancy and close the valve. The bucket vent hole is essential to allow air to escape into the top of the trap for eventual discharge to the main valve seat. The hole and the pressure differential are small, so the trap is relatively slow at venting air. At the same time, it must pass, and therefore waste, a certain amount of steam for the trap to operate once the air has cleared. A parallel air vent fitted outside the trap will reduce startup times. Next, we will discuss the basic water treatment. The purpose of boiler water treatment is to 1. React with any feed water hardness and prevent it from precipitating on the boiler metal as scale. 2. Condition any suspended matter such as hardness sludge or iron oxide in the boiler and make it non-adherent to the boiler metal. 3. Provide anti-foam protection to allow a reasonable concentration of dissolved and suspended solids in the boiler water without foam carryover. And finally, number 4, eliminate oxygen from the water and provide enough alkalinity to prevent boiler corrosion. In addition, as supplementary measures, an internal treatment should prevent corrosion and scaling of the feed water system and protect against corrosion in the steam condensate systems. For the water treatment program, specific doses of conditioning products are added to the water. The commonly used products include phosphates dispersants, which reacting with the alkalinity of boiler water, these products neutralize the hardness of water by forming tricalcium phosphate, an insoluble compound that can be disposed and blown down on a continuous basis or periodically through the bottom of the boiler. Also, natural and synthetic dispersants, or anti-scaling agents, increase the dispersive properties of the conditioning products. They can be natural polymers or synthetic polymers. Also, sequestering agents, such as inorganic phosphates, act as inhibitors and implement a threshold effect. Oxygen scavengers, catalyzed or not, reduce the oxides and dissolved oxygen. Most also passivate metal surfaces. The choice of product and the dose required will depend on whether a deaerating heater is used. Also, anti-foaming or anti-priming agents are a mixture of surface active agents that modify the surface tension of a liquid, remove foam, and prevent the carryover of fine water particles in the steam. The purpose of a cooling tower water treatment program is essentially threefold: to protect the steam against damaging corrosion, to protect the system against damaging corrosion, to control scale formation and fouling, which will impair cooling efficiency, and to control the growth of harmful microbes like Legionella bacteria. As a general rule, the more scale forming a water becomes, the less corrosive it tends to be to steel. This means that provided scale formation can be effectively inhibited, it is beneficial to operate a cooling system at an elevated concentration factor. Therefore, close control of the cycles of concentration is critical to cooling water corrosion control. In effect, you are making the water chemistry work for you rather than having to fight against it. It is also important to control the microbial activity and physical fouling, since both can be a cause of severe localized corrosion. Once these basics have been dealt with, you need a good corrosion inhibitor which is matched to the cooling water chemistry and system metallurgy, and to control its dosage effectively. The scaling tendency of a water supply will depend on the hardness of the water, but if not adequately treated, even relatively soft waters can become highly scaling when concentrated by evaporation. Cooling water scale control is achieved by either removing the hardness from the makeup water using a water softener, or adding a scale inhibitor chemical which extends the solubility of the hardness salts and thus preventing scale formation. An evaporative cooling system is often an ideal growth environment for a whole range of microbes such as bacteria, algae, fungi, and protozoa, which can lead to problems. Effective cooling water microbiological control is not only essential to the efficient operation of a system, but also necessary to control the growth of Legionella bacteria and the risk of Legionnaire's disease. In order to maintain microbial control, effective biocides need to be added on a regular basis and the results monitored using dip slides and periodic laboratory analysis. Next, we will discuss how infrared testing is used. Infrared thermography is a non-destructive technique for detecting temperature differentials that may indicate problems such as loose electrical connections or excessive friction in machinery and mechanical systems. A camera-like device views a large area at a time, senses infrared emissions, and converts the emissions into a visual display. The equipment remains in operation, so production is not interrupted. Hotspots can be pinpointed quickly, saving labor and cost, and targeting plant maintenance where it is needed. Three of the most common applications of infrared thermography are electrical inspections, which is using infrared thermography. A technician can help detect faulty connections in early stages, so possible breakdowns can be avoided. Mechanical. Excessive friction can cause breakdowns if equipment is not lubricated properly. Infrared thermography can help detect problem areas in motor bearings, gears, couplings, pulleys, conveyors, and chain drive systems. Refractory and insulation applications addresses hidden losses of heat that can drain performance and increase costs. Experienced thermographers can evaluate thermal images of walls, ceilings, and roofs for signs of heat either escaping from those areas or entering the insulated space. The next section we'll cover is the function and use of pressure-reducing valves. In a steam-using plant, steam is often generated at high pressures and reduced locally to provide heat for each steam user. This is usually done to minimize the diameter of steam distribution piping and enable more cost-efficient steam delivery. A common way of lowering pressure is by throttling down the size of the steam passageway. For the most basic pressure reduction, it is possible to simply use a conventional globe valve in a fixed, partly open position, or by inserting an orifice plate into the flow of steam. However, any fluctuation in flow rate would be accompanied by a corresponding fluctuation in pressure. To avoid such circumstances, pressure-reducing valves can be used to provide precise control of downstream pressure. They automatically adjust the amount of valve opening to allow the pressure to remain unchanged even when the flow rate fluctuates. While it is possible to maintain a constant pressure by using the combination of an actuated control valve, a pressure sensor, and a controller, a pressure-reducing valve offers the advantage of being able to control pressure through fully automatic self-contained operation, requiring no type of external power source. It can offer the further advantage of extremely rapid response action by immediately sensing and adjusting based on the downstream pressure. In pressure-reducing valves, the mechanism that automatically adjusts the downstream pressure typically uses the balance of forces between the steam pressure and an adjustment spring. At present, this is a universal concept on almost all manufactured pressure-reducing valves. However, there are two different ways in which this mechanism is implemented to control the amount of valve opening. The first is non-piloted, direct-acting valves. The adjustment spring places downward pressure setting force directly on the main valve. The second is a pilot-operated valve, which makes adjustment spring on the spring and places downward pressure settings directly on the pilot valve, which is smaller and different from the main valve. A pressure regulator is a valve that automatically cuts off the flow of a liquid or gas at a certain pressure. Regulators are used to allow high-pressure fluid supply lines or tanks to be reduced to safe and/or usable pressures for various applications. Gas pressure regulators are used to regulate the gas pressure and are not appropriate for measuring flow rates. Flow meters, rotometers, or mass flow controllers should be used to accurately regulate gas flow rates. A pressure regulator's primary function is to match the flow of gas through the regulator to the demand for gas placed upon the system. If the load flow decreases, then the regulator flow must decrease as well. If the load flow increases, then the regulator flow must increase in order to keep the controlled pressure from decreasing due to a shortage of gas in the pressure system. Next, we will go over that heat is measured in BTUs. The British thermal unit, symbol BTU or sometimes BTU, is a traditional unit of energy equal to about 1,055 joules. It is the amount of energy needed to heat 1 pound of water by 1 degree Fahrenheit. The unit is most often used as a measure of power as BTUs per hour. Another important concept commonly seen with BTUs is enthalpy, measured in British thermal units per pound mass. Enthalpy represents the total energy content of steam. It expresses the internal energy and flow work, or the total potential energy and kinetic energy contained within a substance. The advantage of enthalpy is that we can express in one term all of the energy in a substance, which is due to its pressure and temperature. Enthalpy values are used to represent the energy level of steam. By superheating steam, we can add enthalpy to a steam without raising the pressure of the steam. For example, steam at 620 psi and 850 degrees Fahrenheit can do more work in a turbine than steam that is 620 psi and 650 degrees Fahrenheit. Next, we will go through how emergency generators operate. Main power can be lost due to down power lines, malfunctions at substations, inclement weather, planned blackouts, or in extreme cases, a grid-wide failure. In modern buildings, most emergency power systems have been and are still based on generators. Usually, these generators are diesel engine driven, although smaller buildings may use a gasoline engine driven generator and larger ones a gas turbine. However, lately, more use is being made of deep cycle batteries and other technologies such as flywheel energy storage or fuel cells. These latter systems do not produce polluting gases, thereby allowing the placement to be done within the building. With regular generators, an automatic transfer switch is used to connect emergency power. One side is connected to both the normal power feed and the emergency power feed, and the other side is connected to the load designated as emergency. If no electricity comes in on the normal side, the transfer switch uses a solenoid to throw a triple pole single throw switch. This switches the feed from normal to emergency power. The loss of normal power also triggers a battery operated starter system to start the generator, similar to using a car battery to start an engine. Once the transfer switch is switched and the generator starts, the building's emergency power comes on, after going off when normal power was lost. Next, we will review how to safely fire a boiler. There are 4 major categories of catastrophic failure which exist in the boiler itself. The first is meltdown. This is a result of the heating surface metal reaching its melting point. It is a result of the boiler operating on very low water conditions. This by itself will not cause an explosion, but will do major damage to the boiler and create a dangerous situation which could lead to an explosion. Number 2 is thermal shock. This is a condition where low water causes the heating surfaces to become overheated and then cooler water is added. The water then flashes to steam, which expands 1,600 times its volume as water and causes the explosion because there is not enough room for the steam to expand. Number 3 is combustion explosions. These can be a result of gases which build up and an ignition source ignites the gases. This can happen inside the boiler or outside. There are safety devices in place to avoid these situations, and we will discuss these in the following slides. Steam pressure is the 4th one, which is excessive steam builds up which exceeds the design pressures of the vessel. There are also safety devices to prevent this. There are numerous safety features to prevent failures in boilers. Safety valves release steam before a dangerous pressure can be built up. Fusible plugs over the firebox melt at a temperature lower than that of the firebox plates, thereby warning the operators by the noisy escape of steam if the water level is too low to cool the firebox crown safely. Stays or ties physically link the firebox and boiler casing, preventing them from warping. Since any corrosion is hidden, the stays may have longitudinal holes called telltales drilled in them which leak before they become unsafe. Burner controls is a controller and is usually located in front of the burner. On a call for heat, the controller starts a sequence of events that ensure safe operation before the burner is allowed to start. The controller continues to monitor burner operation while the boiler is running. If for any reason the controller senses an unsafe operating condition, it will shut the burner off. Pushing the manual reset on the controller will often restart the boiler. Next, high pressure or temperature switches are devices that is a safety backup to the operator control. It has a manual reset which, when pressed to start the boiler, indicates that the operator control has failed. Next, gas pressure switches on the fuel train. The natural gas fuel train usually has two pressure switches. The low pressure switch locks out the boiler when too little gas is available for operation. The high pressure switch locks out the boiler when the regulator is allowing too high of gas pressure. Both switches typically have a manual reset. Finally, the low water cutoff may have a manual reset when a reset indicates a low water condition has existed in the boiler. Next, we will review how condensate systems function. Often, the condensate which forms will drain easily out of the plant through a steam trap, as shown on the screen. The condensate enters the condensate drainage system. The valuable heat energy it contains can be retained by returning it to the boiler feed tank. This also saves on water and water treatment costs. Sometimes a vacuum may form inside the steam using plant. This hinders condensate drainage, but proper drainage from the steam space maintains the effectiveness of the plant. The condensate may then have to be pumped out. Mechanical pumps are used for this purpose. These are used to lift the condensate back to the boiler feed tank. A mechanical pump, as seen on the screen, is shown draining an item of the plant. As can be seen, the steam and condensate system represents a continuous loop. Once the condensate reaches the feed tank, it becomes available to the boiler for recycling. Next, we will review the various types of steam valves. Some of the various types of steam valves we will be discussing include manual valves, check valves, and bypass valves. Pressure-reducing valves were discussed in detail in previous slides. A valve is a device that regulates, directs, or controls the flow of a fluid by opening, closing, or partially obstructing various passageways. Valves are technically valve fittings, but are usually discussed as a separate category. In an open valve, fluid flows in a direction from higher pressure to lower pressure. Ball valves, butterfly valves, globe valves, gate valves, and diaphragm valves are all examples of manual valves and were covered in the Plumbing and Pipe Fitting Study Guide. Please review that guide for detailed explanations of each. A check valve is a type of valve that allows fluids to flow in one direction, but closes automatically to prevent flow in the opposite direction, or backflow. Check valves are used in a wide variety of locations, but check valves are commonly located at the steam trap outlet side to prevent condensate backflow. Check valves were covered in depth during the Plumbing and Pipe Fitting Study Guide for your reference. Next is a bypass valve. The term bypass valve refers to any valve installed in a bypass line and is not used to indicate a particular valve shape or configuration. So what type of valves are suitable for installation in bypass piping? When considering what types of valves are suitable for installation in bypass piping, it is necessary to think about the role of the bypass line. What was the purpose for the installation of that particular bypass line? Bypass piping can roughly be divided into two categories. Bypass piping that acts as a backup line to allow operation to continue while damaged equipment such as pressure reducing valves and steam traps are isolated and shut down during replacement or repair, or bypass piping whose purpose is to supplement the performance of pressure reducing valves and traps. These different objectives require valves with different features. Therefore, the optimal valve models will be different. Next, let's look at how efficiency of a boiler can be improved. First, let's go over some definitions that will be needed when understanding boiler efficiencies. Heat transfer efficiency is an inherent property of boiler design, and manufacturers typically indicate the values of efficiency that the specific boiler design provides. It is simply a ratio of how much heat must be put into a system to get a given amount of heat out. It should be noted that the manufacturer specifications for heat transfer efficiency for a specific boiler are for a perfectly clean system. Heat transfer efficiency loss can have a very significant impact on overall energy efficiency. Heat loss ratio is also an inherent property of boiler design. Manufacturers typically indicate the values of heat loss efficiency that the specific boiler design incurs. Improvements can most often be made in regard to heat loss ratio efficiency by better insulating the boiler and piping systems. Heat loss ratio is also a value of the building envelope itself, and boilers have to react in relation to how a building loses heat. Improvements in heat loss for a facility should also be looked at when considering methods to improve efficiency. Improvements include better insulating the facility, improved glazing, and better control of airflow within and leaving the building. Operating efficiency, also called seasonal efficiency, of the boiler relates to the actual and ever-changing conditions found within a facility, how the boiler reacts to the load, and the amount of fuel consumed over a period of time. This value is not generally quantified by a boiler manufacturer due to the many variables involved in daily operation, and variables due to the building envelope itself. Since a boiler operates most efficiently when it runs constantly or at full load, the trend of current technologies is to have several smaller boilers managing supply water needs instead of one large unit. This way, each boiler operates closer to optimum efficiency when they are called on for heat. Next, we will go over some various ways that boiler efficiencies can be improved. Properly operated boilers require a certain amount, usually 10 to 20%, of excess air to ensure complete combustion. However, operating with too much excess air reduces boiler efficiency by heating up and throwing away this cushion of excess air. On the other hand, operating the boiler with no excess air can lead to sooting on the fireside, air pollution, poor efficiency, and even potentially explosive flue gases, so that boiler operators tend to have a cushion of excess air rather than a deficiency. Monitoring the flue gas temperature, oxygen content, and carbon dioxide content allows the operator to minimize this cushion and fine-tune the boiler for optimal efficiency under varying ambient and load conditions. Portable or fixed combustion efficiency tests are available from many sources and may be used to manually adjust combustion air quantities. This is typically the only choice for natural draft type boilers and should be performed on a weekly basis. For forced draft boilers, an automatic combustion control system can be added to automatically monitor flue gas combustion and adjust combustion air quantities on an instantaneous basis. Condensate from a steam boiler system is not mineral-free water. Strong consideration should be given to returning all usable condensate in order to minimize the use of cold makeup water, which must be heated prior to entering the boiler. An added benefit will be the decreased use of chemicals and improved boiler surfaces. This will reduce corrosion, which can lead to early failure, and/or the buildup of scale, which can hurt boiler efficiency. Blowdown of boilers to reduce the sludge and solid content allows heat to go down the drain. The amount of blowdown should be minimized by following a good water treatment program. Installing a heat exchanger in the blowdown line allows this waste heat to be used in preheating makeup and feed water. Heat recovery is most suitable for continuous blowdown operations, which in turn provides the best water treatment program. A device like the one shown below on the screen can be attached to the flue to recover a portion of the exhausted heat. This heat can be used to preheat boiler makeup water. Take care not to extract so much heat that the flue gases condense, causing corrosion. If you have a large temperature difference, 20 degrees to 40 degrees, between your boiler intake air location and the ceiling of your boiler room, and this hot air is a result of boiler and stack losses, you can increase your boiler efficiency by either extending the intake upwards or forcing the hot air down. Both options may require a fan and ductwork. If the hot air is due to boiler wall losses, you may want to consider insulating the boiler. If you presently have an old, inefficient oil burner, such as rotary up or atmospheric, or an oversized burner causing excessive short cycling, it may be cost effective to replace the burner with a modern, efficient, and properly sized burner. You may want to consider variable firing rates and or dual fuel capabilities, allowing you to choose the least expensive heating fuel at any given time. Natural gas burners can replace oil burners without requiring boiler replacement. Turbulators are metal baffles inserted into fire tube boilers to increase the heat transfer by increasing the surface area and slowing down the combustion gases. Soot blowers use steam or compressed air to help keep the fireside surface of solid fuel or oil-fired boilers clean. Check with your boiler manufacturer to determine the suitability of either of these measures. You can follow along with our final section of our power plant and boiler review inside the MEC Test Preparation Manual. These questions are pulled directly from the manual, and explanations have been provided to help you better understand the concepts being reviewed in the questions. CAT test question number 1. One reason boiler water is treated is to A, remove waterborne bacteria, B, add chemicals, C, remove solids, or D, make water taste better. Answer C is the best answer here because solids need to be removed to prevent it from precipitating on the boiler metal as scale. Answer A is not correct because waterborne bacteria is typically not a concern and will be killed during steam creation. Answer B is not correct because the answer is not specific enough. Answer D is not correct because boiler water is not used typically for human consumption. CAT test question number 2. Chemical pumps, A, inject chemicals directly into the water, B, pump water through the chemicals, C, measure the amount of chemical, or D, both A and B. Answer D is the best answer here because both answers A and B are correct. Chemical pumps inject chemicals directly into the water and pump water through the chemicals. Chemical pumps use varying methods of providing different amounts of chemicals, but should always be set based on readings received from water tests. CAT test question number 3. Boiler stack temperatures should be A, high, B, low, C, normal, or D, left alone. Answer C is the best answer here. A stack temperature gauge should be installed in the flue outlet of every boiler and monitored regularly to ensure that the temperature is consistent with the firing rate, operating temperature for hot water boilers, or pressure for steam boilers and boiler design. Your boiler supplier or manufacturer should be able to provide data to give you an indication of optimum performance. CAT test question number 4. Visual checks of the combustion chamber are conducted to A. Check for color, B. Check for sooting, C. Check for cracks in the refractory, or D. Determine flame temperature. Answer C is the best answer here because checking for cracks in the refractory is the first indication of ceramic fiber chamber material deterioration. Answers A, B, and C all have to do with the flame mixture and are therefore incorrect. CAT test question number 5. Caution is used when looking for a suspected steam leak because A. Steam leaks may cause severe burns, B. Steam will leak out of the system, C. It makes high-frequency noise, D. It may create staining. Answer A is the best answer here because it directly relates to staff safety, which should always be the highest priority. Though answers B, C, and D could occur, they are secondary to staff safety. CAT test question number 6. Pressure gauges are read and compared to A. Other pressure gauges, B. Logbook entries, C. Temperature gauges, D. Verbal reports of gauge readings. Answer B is the best answer here because the mechanic is looking for trends or changes to previous readings. CAT test question number 7. When using alternative fuels for boilers, adjustments may need to be made for A. Air, B. Water, C. Fuel color, D. Temperature. Answer A is the best answer here because fuels will need a different mixture with air to operate properly. Manufacturer's instructions should always be followed when operating a boiler. Answer B is not correct because water is not mixed with the fuel to fire the boiler. Answer C and D are indicators that do not pertain to the firing of a boiler. CAT test question number 8. General cleaning of a boiler would include A. Cleaning electrical relays, B. Cleaning sight glasses, C. Cleaning the boiler mounting pad, D. Cleaning gas lines. Answer B is the best answer here because cleaning the sight glass directly affects the immediate operation of a boiler. Answer A is not correct because electrical relays would be addressed in an in-depth maintenance activity. Answer C is not correct because it is considered a housekeeping activity. And answer D is not correct because, like answer A, it is not correct because cleaning gas lines would be addressed in an in-depth maintenance activity. So answer B is the best answer here. CAT test question number 9. Preparing a boiler for inspection requires A. Removing all access panels, B. Draining the boiler, C. Opening low water cutoffs and pump controls, or D. All of the above. Answer D is the best answer here because answers A, B, and C are all correct. Inspections require removing all access panels, draining the boiler, and opening low water cutoffs and pump controls. CAT test question number 10. Boiler startup and shutdown requires A. That the operator only listen to the boiler, B. Particular attention to pressure controls, C. Use of manufacturer's instruction and established guidelines, or D. That the operator be well versed in boiler theory. Answer C is the best answer here because boilers vary from site to site, and manufacturer's instructions and established guidelines should be strictly adhered to in order to ensure the safety of power plant employees. Comp test number 11, question number 9. When a boiler is tested at 1.5 times the maximum allowable working pressure, what is the test called? A. High pressure test, B. Vessel stress test, C. Hydrostatic test, or D. Maximum water pressure test. Answer C is the best answer here. Answers A, B, and D are all worded very similar to cause confusion, but the industry uses the verbiage hydrostatic test very specifically, so answer C is the correct answer here. Comp Test 12, question number 9. Boilers with flat surfaces exposed to pressure tend to bulge and warp. What is the proper name of the support device that prevents warping? Is it A, rods, B, stays, C, support arms, D, headers? As seen on the diagram, answer B is the best answer here. Stays are the support devices that help prevent flat surfaces from bulging or warping. Comp Test 13, question number 9. How is hardness in boiler water expressed? A, grains per gallon, B, parts per million, C, micrograms per liter, or D, pH per gallon? Answer B is the best answer here because hardness in boilers is expressed in parts per million. Answer A is not correct because grains per gallon is normally used when indicating hardness in city water. Answer C is not correct because the measurement would be read in milligrams instead of micro. Answer D is not correct because pH is an indicator of acidity or alkalinity. Comp Test 14, question number 9. A Scotch Marine boiler with the burner and the stack located at the front is considered A, single pass boiler, B, double pass boiler, C, triple pass boiler, or D, quad pass boiler. Answer B is the best answer here, as indicated by the diagram of a 2-pass boiler on the screen. Comp Test 15, question number 9. The height of the water in a boiler sight glass should be A, halfway up the sight glass, B, higher than any part of the boiler exposed to excessive heat, C, covering half of the top row of tubes, or D, 2 inches from the top of the sight glass. Answer B is the best answer here because the safety concern is that all parts of the boiler that will be exposed to heat will have enough water covering it to remain safe. Because boiler manufacturers build boilers differently, answer A and D are too specific and do not ensure that all the appropriate parts are covered. Answer C is not correct because it exposes parts of the boiler that could contain excessive heat and would therefore place the boiler in an unsafe operating mode. Comp Test 16, question number 9. If the supply of makeup water to a boiler was cut off, the main protective device that would shut down the boiler safely would be the A, thermal overload, B, low water cutoff, C, pressure relief valve, or D, thermostat system. As shown on the diagram, answer B is the best answer here. Boilers are equipped with low water cutoffs as a safety feature to shut down the boiler in the event makeup water is lost. Answers A, C, and D all have to do with temperature or pressure safeties and do not pertain to water level. Comp Test 17, question number 9. When a boiler is equipped with a gate-type blow-off or blow-down valve and a cock or quick opening valve in the same blow-off connection, which valve should you open first? A, the quick opening valve, B, the gate-type blow-off valve, C, both valves at the same time, D, neither valve. This operation requires another procedure. Answer A is the best answer here, because the slow opening valve does not produce sudden changes in flow, and therefore you can crack the valve to warm up the piping slowly. The proper procedure is, number 1, open the quick opening valve. Number 2, open the slow opening valve. Number 3, blow down the boiler for the amount of time specified by your water treatment consultant by opening and closing this slow opening valve. Pay close attention to the water level in the gauge glass. Some loads require several short blowdown cycles to maintain the proper water level in the boiler. Number 4, close the slow opening valve. Number 5, close the quick opening valve. Number 6, open the slow opening valve again to drain the line between the quick and the slow opening valves. Number 7, close the slow opening valve again and double check that the shutoff is tight after the valve has cooled off. Note, never pump the quick opening valve to blow down the boiler. Such action could cause water hammer and damage piping and valves. It could also cause personal injury. Never leave an open blowdown valve unattended. Remember, the valve closest to the boiler must be open first. Comp Test 18, question number 9. An absolute pressure of 14.7 psi is equal to a gauge pressure reading of A, 0 psig, B, 12.1 psig, C, 14.7 psig, D, 29.92 psig. Answer A is the best answer here because the absolute pressure is measured relative to the absolute zero pressure, or the pressure that would occur at absolute vacuum. The equation is shown on the screen, providing a gauge pressure equal to 0 psig. This completes our power plant and boiler module of the SEASHI MEC study guide.